Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm pleased today to welcome Mark Johnson, who is going to be talking to us today about building natural language parsers. Many of you already know Mark. He spent last year here as a visiting researcher and has a lot of friends, I think, in the group and elsewhere in MSR. Mark, we sent him back to college, and 3 months later, and he's back again now for a visit. I think he said something about laundry, but I don't know. We'll see about that. Anyway, Mark is a very eminent presence in the field of natural language processing. He, in 2003, was president of the ACL, which is the premier body in the field. And he has a very extensive list of publications, and I turn things over to Mark.
Great. Thank you. Thanks very much. Yeah, I've only been back at Brown for 3 months since being here, so most of this material is actually stuff that I think many of you have already heard bits and pieces of. But I think I've sort of put it together in a slightly novel way. There's also some, let's see if I can get this thing. Yeah, there's also actually some new material here when I'm starting to talk about, ooh, that's weird. I don't know if there's any chance on my screen. There's the thing is showing up fine.
Yeah, sorry, the rooms are still not quite
Switch to laptop 2 on the touch screen, and then switch back to 1.
Okay, the touch screen is black.
Okay, it'll come on live when you touch it.
I see. Okay, so laptop 2.
And then switch
back. Terrific. Isn't technology wonderful? Yeah. Okay, all right. Yeah, that'll actually teach me. I try to squeeze as much material. I mean, I sort of figure with these displays, why have margins, right? And I guess the reason why you have margins is, yeah.
I think you need to take a large margin approach.
That's right, exactly, yeah. Okay, all right, so just to make sure we're all on the same page here, I'm talking about parsing as essentially recovering syntactic structure, the way words combine to form phrases and sentences, and maybe also identifying dependencies between these words and phrases. And a grammar is really nothing more than a finite specification, some finite way of describing generally an unbounded or an infinite set of syntactic structures. The reason why I sort of stick this up here is because it's actually not uncommon, particularly when I'm talking to machine learning people, that they'll say, sure, I think it's fine to try and learn what the possible phrases of a language are, and I think it's also fine to sort of try and characterize that in some finite way, but this grammars and parsing stuff I don't really want to do at all. And what I want to say is, well, actually, anything which is a finite specification of the way, as I said, you form phrases out of words, you've got a grammar, and if you've got a computational process that recovers those structures, you're doing parsing. Okay, so of course what the machine learning people usually mean, so maybe it's just as well this isn't here, because this slide is making, well, it was actually sort of saying that I think what, the skepticism about parsing is usually associated with is parsing in the classical AI perspective, which is where parsing is, so usually, in fact, the way in which parsing was sold was that parsing was mapping from sentences to their meanings, and it was sort of part of this classic AI story that once we could compute meaning representations, then we could do general inference with it, and that in fact actually essentially parsing was the bridge that would let you map from natural language into sort of classical AI inference. The problem with that, of course, is that we never really actually knew what meaning was. In fact, what I say on my slide here is, those sorts of parsers maybe weren't completely reliable, but in fact, I think actually the bigger failure was that we really didn't have an idea of what a meaning representation was supposed to be. And once we sort of turned to probabilistic parsing, there really are two main uses of parsing. One is producing parsers essentially as, for the structures themselves, where you actually use the syntactic parsers. And so a classic application there would be in sort of classic machine translation, where you take an English text, parse it to produce an English parse structure, and then somehow do some sort of tree transformation on that to produce a French parse structure, and then from that generate a French text. So that tree transformation might be, say for example, treating the tree as some sort of mobile, and then permitting nodes to swing around. I guess one application, where essentially what I'm trying to say is I think there's actually two ways of using probabilistic parsing. One way is using the representations which are producers. Another way is to actually, in a sense, sort of throw away the parsers and just actually use the parser itself as a clever language model. I'll actually be talking about two applications and that do use parsing in these two alternative ways. One thing I would like to suggest is that I think that parsing in terms of recovering representations is actually likely to play a bigger role as we start to look at information retrieval and question answering with devices where there's limited bandwidth. So I'm thinking of handheld computers that you might want to talk to. I think the standard reasons for why parsing is not useful for, say, doing something like web search is because the queries are usually too short. There's very little syntactic structure in them. And with large displays, we can, in fact, return an entire document. We can actually let the user interpret the answer. But once we start to try to talk to our computers and have them talk back to us, I think the fact that we can talk to them means that we can use we can actually provide richer input to the machine. It's much easier to say a full sentence than it is to type it. And I think also if the machine's going to say something back to us, or even just sort of display it on a tiny screen, displaying a full biography of Bill Clinton is not really a terribly useful thing if what you want to do is get the information about when he was born, for example. Okay, so I'll just continue. So this is basically saying what I was saying before. I actually do think that this is worthwhile looking at. I mean, it's in other words, connecting parsing with speech and using it for question answering or information retrieval. I think it's a longer-term research goal, but I think with a lot of these things, unless we do it, it won't get done. So now I'd like to say a little bit about, as this is really sort of introduction to this material here, which is saying, which is sort of describing what I believe is the state of the art in terms of natural language parsing. I'd like to explain how I actually got to this coarse-to-fine parse rescoring approach. And that came from actually worrying about the question of whether we could actually combine the sort of rich handwritten grammars that were in the style of the mid to late 1990s, which had some pluses. In other words, they could sort of capture very rich and detailed representations, but had a lot of drawbacks, as you can see there, with the generative probabilistic parsers, which were at that stage just being developed, and they had really a number of really sort of great advantages, including one of which, and I actually think this is very important, the fact that they could actually be learnt from data. So I was wondering, was it possible to actually combine these two approaches? These generative statistical parsers that I was just talking about fit within what Magerman actually called the history-based approach. And so you can understand those parsers essentially as constructing a parse tree or generating a parse tree on a node-by-node basis but the prediction of each node was conditioned on a certain part of the history of the previous derivation. What I'm actually showing in this tree here is showing the information that the Charniak parser uses when it's predicting the word price, the word in red there, and that's actually conditioned on all those nodes that are in blue there. So in fact, there's actually and every single node in the tree has been predicted in that way. So in fact, actually the prediction goes top down, left to right, and it's also, actually not left to right, it's head driven. So in fact, you can see here, for example, the word price is the head of that noun phrase, and that's in fact actually going to be predicted before the determiner the is in fact actually generated. And it's conditioned on the fact that the verb that governs it is the verb raised, for example. And in a sense, these models, well, not in a sense, these models assume that each node is independent of all of the existing structure, all the structure that's been generated so far, except for the nodes explicitly conditioned on. And that actually then means that the probability of the entire tree is a product of the probabilities of generating each of the nodes. And that actually means that estimation of these probabilities is in principle straightforward. So the maximum likelihood estimators are just the relative frequency of the co-occurrence of price, the frequency of the occurrence, say, for example, of the noun price in that conditioning environment. You'll see over there, there's a caveat, and the caveat is that the black magic involved here is smoothing. With this many conditioning events, you face tremendous sparse data problems. And in fact, the performance of these parsers is largely dictated by how well one can do smoothing. Okay, so putting on a linguist hat very temporarily for about 1 or 2 slides. What a linguist would say when they look at these at those sort of generative models is to say, yes, well, that's all very well and good, but real linguistic structures actually exhibit cyclic dependencies. So you can see over here I've sort of depicted a very simple dependency structure for a sentence like Sandy bought the wine that Sam likes. So the point here is that Sam likes is a relative clause that modifies the wine, and so that's indicated by that mod link over there on the left-hand side. But the wine is also the direct object of the verb likes, right? So what is it that's liked is the wine. I also picked this because I realize that many of you are actually going to understand this as being like a Bayes net. In fact, actually, this is not meant to be a Bayes net, but of course, Bayes nets with cyclic loops in them are very tricky things themselves. So just simply, again, sort of just simply trying to understand the generative structure of something like this in terms of generating these things node by node, in that sort of incremental fashion, is certainly a very difficult thing to do. In fact, as I said, the naive approach winds up double counting the word wine, right? So in other words, if you generate wine first of all as the direct object of buy, and then again as the direct object of likes, you essentially have double counted the probability of generating the word wine. And really, this problem of the lack of independence of the generation actually makes, as we'll see, estimation of such grammars computationally much harder. So if we want to actually move to a framework where we're going to permit there to be these types of reentrancies or cyclic dependencies, we really sort of need to move away from Bayes net type formulations and move towards Markov random field frameworks. In fact, the basic idea is sort of relatively well known. Like all really good ideas, it's been invented many different times and in fact comes under many different names. So MaxEnt, Loglinear, exponential, Gibbs forms, they're all, from my perspective, they're all basically the same mathematical framework. And the key thing is, I'll actually explain that basically everything to the right over here is really very similar to the basic generative framework that we were looking at before. The problem is that because these factors are no longer independent, in general we're going to need a normalization constant, the partition function z. And I've highlighted that in blue there because that's the thing that in fact actually is going to cause us lots of problems. And as we'll see, once we no longer require the factors, that is the probability of a tree to be a product of independent factors, independent generation steps. It'll turn out that our parsers no longer need to be trees. Our features can be any computable function of the parsers. So we can have one feature for each different type of linguistic dependency. So it certainly is a nice framework for capturing those rich linguistic dependencies we were talking about before. But the price that we pay is that the simple relative frequency estimators for the feature probabilities or the feature weights no longer works. And as I said, I'll explain that right now. So the first thing I want to note is that this type of log-linear framework is at least as expressive as the generative framework that we were looking at before. So, and one way to see that is that we can in fact actually define features that corresponded to exactly the conditioning contexts and nodes that were being predicted in the generative model. So in other words, if I define a feature that just simply consists of the conjunction of all the different events that the conditional probability was capturing in the generative model that I was showing before, right? And so this feature is basically going to say it's going to indicate the number of times that this context appears inside of the parse tree. Then if I assign that feature a weight, which is the log probability under the old generative model, then it's actually possible to show that, and so here's the example of it, then it's actually possible to show that the generative and the log-linear models actually define the same probability distribution. The big difference is that it's actually easy to add additional features to the log-linear model, but it's very difficult to add them to the generative model. So we'll actually see later in the talk that a very powerful piece of evidence for the fact that a noun phrase is actually beginning at this position here, has its edge right here, is the fact that we see a verb that's followed by the word the. It's actually fairly hard to see how you would change the generative model, that story I was telling you before, so it could capture that sort of dependency. Because in fact, actually, that really sort of cross-cuts many of the conditional probabilities that were being used before. So one big plus of the log-linear approach is that it's actually very easy to just simply incorporate new features, and we'll actually see that being used. Whereas in the generative model, you really have to rework all the different conditional probability distributions. Okay. I've just been stating that maximum likelihood estimation is in fact actually very hard. I'd like to try and see if I can give you a bit of a feel for why that's the case. So in general, when we try to estimate the weights on these features or the probabilities of these features, the most straightforward is to do it when you actually have labeled training data. In other words, a tree bank training corpus up there, D. And what we really want to do is simply adjust the feature weights or feature probabilities to make the training corpus as probable as possible. And the problem is that the probability of a single tree, as I said, has got this normalization constant Z sitting out in front of it. And that normalization constant Z essentially involves a sum over the set T, this script T, which is the set of all possible trees for all possible strings. And natural language being what it is, I mean, there's an awful large number of strings out there that have non-trivial probability. If it didn't, natural language wouldn't be such a good thing for communication. Basically what the maximum likelihood estimator tries to do is to adjust the feature weights to make the trees and the training data more likely than any other trees. Now, if the features actually happen to form a tree of independent generative steps, then this partition function Z is going to be 1, and that's essentially going to yield an easy estimation problem. But if the features have complex dependencies, then the partition function Z isn't 1, and that causes essentially, whenever I adjust these feature weights, this Z may change, and so it may change the scale of these probabilities in an arbitrary way. Now, it turns out for parsing, what we're really interested in is finding the most likely parse, this T hat of S for a string S. And that really is just simply the argmax of, in other words, we're just simply looking for the most probable tree given S, where T of this script T of S now is a different set of trees. It's the set of possible trees for the string S. And it's actually easy to show that this conditional probability is in fact actually written in this form over here, where the partition function now no longer involves a sum over all possible trees, but in fact only involves a sum over all trees for the string S. That's for this point down here that I'm making. This actually makes estimation far easier if you're just simply trying to learn the conditional distribution. So this is also sometimes called discriminative training. And so it actually turns out that discriminative training is actually computationally easier than doing the full, the full training for the joint distribution over strings and trees. And as I said, so conditional maximum likelihood estimation in fact actually optimizes the feature weights to optimize the conditional probability of the training data. And yeah, that was basically, I think, sort of what makes this conceivable at all, computationally tractable at all, is the fact now that instead of actually having to compute these partition functions and expectations over the set of all possible trees, if all I want to do is actually estimate these conditional distributions, then in fact I really only actually have to compute my expectations over the set of trees for the alternative parsers in the training corpus. And so here I'm trying to give you a little bit of a picture of what this conditional estimation really means. So if you imagine our training corpus consists of a set of sentences and parse trees, then our tree bank training data tells us what the correct parse is for each of the sentences. And so we've got our feature functions. We can apply them to those parse trees to get a feature vector for the correct parse tree. We can then run our parser on the sentence and then obtain the feature vectors for all the other parsers for each of these sentences over here. And the feature extractor extracts features for those too. And then basically the job of training is to select feature weights that make each of these vectors here score highly compared to all the other vectors for that same sentence. And basically what we want to try and do is find weights so that we can select the true parse for each sentence and discriminate that from all of the false parses. And this, so long as the number of these feature vectors over here is small enough so that we can enumerate them, this actually is, a procedure which at least is starting to look computationally feasible. There's in fact the difference, I want to sort of say a little bit more about the difference between trying to do joint estimation, in other words, which is what the generative models try to do, and what this conditional estimation tries to do. So standard maximum likelihood estimation is just simply trying to maximize the probability, essentially, of the trees and the strings together. And so this actually means that the models that you get out from that can be used for language modeling, as I was saying before. That's one of the applications of parsing. And the way in which you do that is, given a string S, you compute the probability for all of the trees that correspond to S, and then essentially sum those probabilities, and that gives you a probability for the string S. And because we can compute the probability of a string, this actually means that we can, at least in principle, extend such a framework to unsupervised estimation where you're given the strings alone. That's essentially what an EM procedure would do for you. Conditional estimation instead tries to maximize the probability of a string, of a tree given the string S. Instead of the joint, it's maximizing the conditional. This is exactly what we need for parsing. And in fact, I think you can make the argument that there's a very powerful argument that says that you should optimize the thing that you really care about. In other words, if what I'm interested in trying to do is parse, then I should try to learn the conditional distribution. It's interesting because it actually uses less information from the data. It ignores any information about the distribution over strings. You can see up here, right, that the joint is factored into the conditional times the marginal. And conditional estimation ignores that marginal distribution over strings. And in fact, one thing which is sort of very strange about this is that this conditional estimation, in fact, actually learns absolutely nothing from unambiguous sentences, which is from a cognitive perspective, it's actually very strange, right? Here's a sentence, there's no ambiguity in it whatsoever. But of course, if all you're trying to do is to disambiguate ambiguous sentences, well, this sentence isn't ambiguous. So what can I learn from that? Yes?
Well, in that framework, is there any reason why the features could not be external to the sentence?
We've actually done some experiments on that, trying to use features which are... This framework is, in fact, general enough to be able to handle that sort of stuff. We've done some information trying to condition on external contextual features. So one of the things that you think might... In this game, we try to see if we can go for the low-hanging fruit, right? And the thing that we were thinking of was to say, gee, maybe it's the case that in a text, if there's just been a question, you might be more likely to see a noun phrase as an answer as against a full sentence. And so we were just actually trying to condition the top-level structure of the parse based on whether the preceding sentence actually ended in a question mark or not. But we couldn't get any positive results with that. But that was, so yes, in principle, you can do that. In practice, we haven't found any way of using any features which actually turn out to be useful. Yeah, John?
For your applications like in machine translation, how important is finding a map or the top end versus having a calibrated probability to given errors?
Good question. In fact, I think in general, I mean, there are people in this room that actually may know far more about machine translation and parsing than I do. I think it's fairly standard to throw out the probability distribution and just simply keep the map parse. And I think part of the reason why is because, as you'll see, in the actual parser that we deploy, we're really optimizing finding the map parse. That's the objective that we're really shooting for. Yeah, I mean, what's going to happen? I mean, this is leading to a series of approximations which will lead to the actual parser that we use. So anyway, what that means is that you can't really trust the probability. I mean, we actually tune the parameters so that the where is it? The argmax guy down here is right as often as possible. And to be honest with you, I really don't care whether the relative probability between that guy and the next guy in the list is accurate or not. But maybe we should, right? No, because then, I mean, the fact that we don't care about that actually means that I think if we try to actually believe this probability, there's no real reason to believe it. But if we really do care about this as a probability distribution, maybe we should actually be taking seriously our probabilistic objective. Right. Yeah.
Logistic regression doesn't have that property that the unambiguous. I mean, it all depends on how you set it up, but I could imagine that stacking the deck would give you a bunch of clear cases. If they lend some insight about some internal feature that shows up somewhere else in an ambiguous one, they would have an impact.
So logistic regression.
You're saying it's not really this new.
Yeah, so logistic regression, I mean, I guess it depends on whether you're thinking about logistic regression predicting a continuous variable or a categorical variable. So this is like predicting a categorical variable where there's only one outcome.
Right, but if any of the...
In which case you get it right anyway.
Well, you get this one right, but what if there's a feature inside of here that applies in some other case?
So I'm putting this up to say that, in fact, I think this is fairly unnatural, right? So in other words,
So you want a model for which that isn't so.
Yeah, exactly. So I mean, I believe that the received wisdom in machine learning is that discriminative training beats generative training hands down. And I'm saying, yeah, in fact, in general, I think that's the case. But let's remember that it does, in fact, actually do a few strange things. I mean, certainly, sitting in a cog-sci department, I talk a lot to real psychologists and people studying child language acquisition. And they believe that these sentences ought to be the most informative of all, right? The ones where there's no ambiguity. And I do think it's rather strange. And in fact, I actually think a big part of when one ought to expect joint estimation versus conditional estimation to do better really has a lot to do with whether you actually believe your model or not. And I think this will come back when I start to talk a bit about self-training. Basically, I think if you if you believe your model, so remember these two probability distributions both depend on the model parameters. And if they both depend on them in the same way, then optimizing this with respect to the feature weights ought to actually improve the performance on this. On the other hand, if you don't believe your model, and to be honest with you, you'll actually see some of the models that we use, I'm not so sure you should believe them, right? Then in fact, actually, there's no real reason to expect that optimizing the features to optimize this should optimize this at all. I mean, these are two different distributions, right? Okay, all right. Next thing, and this is sort of kind of like the last point I really want to make in this sort of general introduction here, is to say that starting to think this way actually led us to realize that really these models are really only making decisions based on the feature vectors that are computed from the trees. And so the actual choice of the representation really doesn't matter as long as the tree is rich enough to actually define the features that we really care about. So if this is the linguistic representation that we were trying to shoot for, you could sort of say, well, actually, what information is this coding? This is coding the fact that you've got a relative clause hanging off wine and that wine is the direct object of likes. Well, the sort of somewhat more superficial parse tree representation over here encodes that same information in this blue structure over here. So in other words, whenever you see this blue structure over here, you're actually going to see this same configuration over here. So, and so you could imagine, in fact, actually computing exactly the same values for the features from this representation instead of from this one. Given that that's the case, there's really not much point to bothering to work with this. I mean, because the probabilities are going to wind up being exactly the same if the features are the same. So, and this is just basically saying the same thing here as well, right? So, I know there's a number of people in the community that don't necessarily believe this, right? I mean, the power set group is really betting on the fact that there's really something to be gained by working with LFG-style representations. But here I'm sort of basically making the argument that the way in which they get their training data is in effect by taking the Penn tree bank, which is a set of hand-constructed, relatively superficial parse trees, and then mapping them automatically to their more sophisticated representation, and then defining a log-linear model based on some features computed from that more sophisticated representation. And the point that I want to get at here is, in fact, actually this is exactly identical to working directly with the Penn tree bank trees if we define our features as the composition of their translation operation and their features. And so, in fact, actually this is just a hunch, I can't prove this, but I would expect that there's really no significant advantages to working with more sophisticated linguistic representations, so long as the training data is basically just Penn tree bank based. So based on that, I sort of started to say, well, gee, maybe we should really just work with these Penn tree bank trees. I mean, so that is the linguistic sophistication should go in the design of the features. Now I want to sort of switch gears a little bit and sort of describe how this computational framework is actually going to work. We left it where we said, by doing conditional estimation, if we can in fact actually enumerate all of the possible parsers for a sentence, then maybe we can actually compute the partition functions and the expectations we need for training. In fact, actually, if you try to do this on a really broad scale, even just simply enumerating all of the possible parsers becomes intractable. I actually did a calculation of the number of possible parsers of a relatively sort of standard sentence in the Penn tree bank, and it was working, like 10 to the 60, 10 to the 70, something else like that. So, a number that's way too large to try and enumerate exhaustively. So instead, actually, what we wind up using is this idea of coarse-to-fine computation that, in fact, my colleague Stu Gieman at Brown proposed. He was thinking of coarse-to-fine computation as being something that you would use for vision. So he was thinking that you start off with sort of viewing the scene from a large distance. So all you really get to make out then are the coarse grain aspects of the scene. And all the objects are fairly small in terms of numbers of pixels. As you move closer towards the object, the image gets larger, there's more pixels associated with every object, and so you sort of start to fill in detail. And so for computational linguistics, the way in which we've applied this idea is to essentially define a hierarchy of increasingly more complex models. And the idea is going to be that we use the coarse-grained models to constrain the search space of the succeeding finer-grained models. The idea being that each succeeding model filters and elaborates the output of the preceding models. And then a key point to note here is that this conditional estimation I was just talking about fits in well with coarse-to-fine computation, where now we're in fact actually in a sense going to condition each model's, essentially each model takes the output of the preceding stage as its conditioning context. So I'll see if I can explain that a little bit better. This is actually how we apply it inside of our parser. So as I said, it's infeasible to directly search for the most probable parse. So in fact, actually what we wind up doing is something over here. In fact, actually, we take the input sentence, we run it through a fairly simple context-free parser, and it produces a parsing chart. And its job is just to identify where nodes, where constituents might be and where they might not be. We use that parsing chart to constrain the search for the generative parser. And then we can use a dynamic programming algorithm to read off the 50 best parsers from the generative parser. And then the model that I was just talking about before, Loglinear parse rescorer, and it's now only looking at 50 parsers. So in other words, its job is out of this set of 50 parsers to pick the best one. 50 parsers is small enough so in fact we can calculate these partition functions and expectations directly from those sets. Makes that computationally quite tractable. In general, it takes around a second to produce these per sentence, and it takes, depending on the number of features inside of the parse rescorer, somewhere around 1/10 of a second to another second to compute that. So here's another picture of that. So now we're sort of imagining that the generative parser is just simply producing 50 best parsers here. We apply our feature functions to those to compute 50 different feature vectors corresponding to those 50 parsers. At this stage, we're assuming that we know the weights, so we can now compute the score for each of those parsers. And then essentially we wind up taking an argmax of those. Then the best scoring parse is the one that is then predicted to be the correct parse. The key thing down here in terms of training is that now the partition function, the thing that we need to compute our expectations over, are essentially these feature vectors over here. And as I said, 50 seems to be a decent number for that. So here's part of the argument for that. If we actually take a look at, if we think of the number n as being like a beam, you can actually ask, okay, how does the accuracy, and we're measuring it using an F-score measure here, how does the accuracy change as we increase the number of parsers? So of course it would be ideal if the accuracy went up to 100%, but it doesn't. It's not clear that it really can, because I think there's actually a certain number of errors, just simply labeling errors in the Penn tree bank, and we're unlikely to ever get those right. But you can see, we get around, the error rate drops to around 4%. If you could, this is what's sometimes known as an oracle score. If you had some magic way of picking the best parse out of this 50 best parsers, you'd get around 4% wrong. Yeah.
So how sensitive is this code to the source of the data? So you just try to compare
I actually haven't done that, so that's a good thing to do. We should really do that for the Brown corpus. I mean, for example, or switchboard. That would actually be a great thing to do. Yeah, go on.
Yeah, so I was just wondering, is it actually necessary for the first parser to be generative, or could it be conditionally estimated? I mean, could it be a Loglinear model with features but decomposed in such a way that you can actually compute?
Well, so in principle, yes, it could be, right? I mean, in principle, we could just simply treat this as just a set of parsers that are produced by some other process. It will actually turn out that it's very useful to incorporate the log probability from the preceding stage as one of the features in the next stage. This, in effect, sort of guarantees that each stage is never going to be worse than the... I mean, one of the things that you really want to ensure when you have one of these hierarchical models is that you're not losing, you know, as you're moving up through complexity, right? If you can incorporate the log probability from the preceding stage as one of the features in the next stages, we've actually found that that seems to ensure that even if your choice of features at one level is really pretty bad, you're unlikely, very unlikely to do any worse, to do any damage by adding one of these stages in there. Yeah, I guess, what is it? The Hippocratic Oath. First, ensure that you do no harm. I mean, I think that's true with these machine learning things. Yes?
Is there any way to think of the gap in performance that you're gaining systematically in terms of what are the errors that are being corrected that you're not able to?
I've spent a lot of time staring at what the parser gets wrong. So the received wisdom is that the parse failures are kind of like global failures, you know, and so when things go wrong, they go wrong, terribly wrong. I cut out from this, just cut out right now, you know, pictures of some of the parse failures. In fact, actually, this parser is now getting good enough so that oftentimes the failures are things just simply like prepositional phrase attachment or misanalysis of coordination. So there's often only really one thing that's wrong in the tree. So, and these things are often, you know, associated with semantics. In other words, to really know what the correct analysis is, you really need to know what the sentence is. I think semantics is the big open question in this whole area. I mean, I think that's really what we're sort of dancing around. I think, in fact, a lot of the lexical statistics that we're collecting are really just serving as a proxy for semantics. And that's, I think, one big reason why I think we need to try and learn from lots more data. But to really actually understand semantics, I think would be, I mean, that would, I think, actually be a major breakthrough. Okay, this is also just sort of showing some evidence that the beam of 50 seems to be wide enough. In fact, actually, just before this talk, I did another run with a beam of 100, and the performance, the overall parser performance was unchanged. And 100 is about as big as we can do in 16 gigs of RAM. So, okay, all right. So this conditional estimation in terms of parse rescoring with this coarse-to-fine method actually is relatively easy to use. You can actually use it with very large numbers of features. We run with somewhere between 1 to 2 million features. We deal with overfitting by regularization. And there's at least 2 different ways of doing that with either L1 or L2 penalty terms. And there's some very interesting work that Gallon and Zhangfeng have been doing about that. In fact, actually, I've been experimenting with over the last month or so. There's a couple of more sort of minor technical issues here. One is that the 50 best list probably, I mean, may not include the true parse. And so the basic idea is going to be that we'll actually train the rescorer to prefer the parse in the candidate parse list that's as close as possible to the true parse. So that seems sensible. I mean, you know, there's no way at runtime you're going to be able to pick a parse that's not in the 50 best candidates. Things get a little bit trickier when you try to do this because, in fact, it can turn out that there are several parsers in the 50 best list that are equally close to the true parse. And this, in fact, actually leads us to posit an EM-inspired non-convex loss function, which I'll show on the next slide. I'm putting this up here because, in fact, I'm hoping if Gallon could think about extending his optimizer to deal with this sort of case, that would be great. So here's the loss function in some more detail. Q is the loss function we're going to try to minimize. It's the negative log likelihood, plus in blue you're seeing over there, a penalty term for the regularizer. Here's the log likelihood. You'll see essentially we need to sort of compute this over this set T star, which is the set of parsers in the 50 best list, which are as close as possible to the true parse. This is the EM style loss function here. So in other words, and I think this is in fact actually not such a crazy loss function here, because what this is saying is, look, in fact, I really don't care which of these very good parsers you wind up picking. You should get credit for those. What's also neat about this is that in terms of this is sort of diving down into details here, which I've tried to avoid a little bit in this talk. But basically, if I take a look at this term up here, that turns out to actually be a ratio of two partition functions that are computed over two different sets of parsers. There's the partition functions for each defined as the set. The statistics that you need to optimize something like Q depend on the derivative of the log likelihood. That turns out to be a difference of two expectations that are just simply computed over these two different sets. And as I said, because these sets are finite and small, it's fairly easy to compute those expectations. And almost all the time in training is actually spent in computing those expectations. So in fact, I'm very interested in looking at ways of parallelizing this computation. Okay, so we're now at a situation where the parse rescorers features can be any computable function of the parse. The choice of features, in fact, I actually think is the most important aspect of parser design. The features can be based on a linguistic theory. In fact, if you have two linguistic theories, you can include them both, right? And they needn't be. In fact, as we'll see, a lot of the most useful features are what I call shotgun or Hail Mary features. And the reason why I call them that is because the way in which I imagine, I'd go hunting is over there. Point roughly in the direction and pull the trigger and hope that you hit something useful, right? I gather Hail Mary is the football term for doing something similar to that, right? So, and we'll actually see that in fact, there's another comment to Galen. I actually think we might want to regularize these two things differently. It might be very useful to do L2 up here and L1 down here. And so that might be something that would be also worthwhile looking at adding. Okay, down here there's some information here about feature selection. As I was saying before, one general thing that we do in this coarse-to-fine computation is to include the log probability from the previous level as one of the features. And so that really means that this sort of rescoring should never really hurt the overall quality. I mean, as I said, the thing you really want to avoid is having a step in the pipeline that is moving backwards. As important as I think the features are, I actually think one of the really big sociological problems in the field is that we really haven't found a way of communicating information, things that we've learnt about features. I mean, the problem is that I believe that they're very important, but they're also really boring to talk about. It's virtually impossible to get a paper published on it. And I don't blame it, because it's actually really boring to hear people talking about it. So I'm only going to give you two features here. This is a feature which is sort of linguistically inspired, things that I call byhead features, which are essentially like these dependencies that we were talking about before. So the feature is a C++ class, which actually takes a tree as its input, and it actually sort of extracts all of the head-to-head dependencies. So it would extract, for example, the fact that date appears in this configuration. And in effect, it's sort of really learning that date can serve as the subject of the passive verb set, right? And so we've got about 70,000 of those after pruning. Here's an example of something which is sort of somewhat closer to one of these Hail Mary or shotgun features I was talking about before. So for every constituent in the parse tree, we record what I sometimes call edge features. So for this noun phrase over here, I'd record the fact that at its left boundary we've got the, and that's immediately preceded by the preposition over. And it turns out that things like that are a very powerful feature for predicting boundaries, say, for example, of noun phrases. If you see a preposition followed by a determiner, there's probably a noun phrase that begins there. And this is an example of the sort of feature that would be very hard to incorporate into a generative parser. Okay, I think if I can take a little bit more time because of all the futzing around, I'd just like to sort of very quickly go through an application of this coarse-to-fine parsing for speech error detection and correction, which I think some of you guys, Greg has seen, for example. Okay, so I'm going to show essentially how we can use the parser, this conditional parser, essentially to detect and correct speech errors, at least in some contexts. So the traditional typology of speech errors includes things like restarts and repairs that are shown up there, fill pauses like the R's, and then parentheticals. And the idea is that if you want to actually work with spoken language, you probably want to detect these things and excise them if you can. Liz Schreiber classified repairs as consisting of a referendum, the thing that gets repaired, an interregnum, which may consist of 0 or more fill pauses, and then the actual repair itself. And one of the things that makes it difficult is that the referendum is typically not a syntactic phrase, so you get isn't a full phrase. The interregnum is lexically and prosodically marked, but needn't actually be there. And then the thing that we actually built off was to say, look, actually the referendum is often a rough copy of the repair. So in other words, you can see you get and you can get seem very similar to each other. There is a tree bank corpus of this, the switchboard corpus, and it contains parsers for about 1 million words of spontaneous telephone conversations. And the referendums are indicated by edited nodes. So the very first thing that we did was just to simply take this tree bank and feed it into the parser that we've got, the parser training procedure, and then try to see what happens if we parse sentences like this. We get some very curious looking structures. It turns out they don't actually contain any edited nodes whatsoever. And of course, if the generative parser never posits any, the rescorer certainly won't find any. So something is clearly wrong here. In fact, if you take a look at this, right, you actually look at the dependencies in a typical speech repair. So this is one of the classic ones that Liz Schreiber worked on, right? I want a flight to Boston, I mean to Denver. There certainly are dependencies here, but these dependencies are crossing dependencies, which are in fact actually not typical of the sort of tree structures representations that we're dealing with. So context-free grammars and tree-structured representations in general are very good at capturing nested dependencies and very bad at capturing crossing dependencies. In fact, the solution that we're going to adopt is going to be to build a specialized transducer whose role is going to be to incorporate these crossing dependencies. And I'd be very pleased to talk about that. In fact, I'm not going to talk about that here because parsing is the application here. But the basic idea is going to be that what's left over after you excise the referendum and the interregnum reads just like a perfectly good sentence. Right? So what's left should have high probability under a parsing model. And so we're going to use a model of normal language to help us interpret ill-formed input. So in more detail, we're going to adopt the noisy channel model, which consists of usually is a good thing to do to actually adjust those mixing weights. And then, of course, once we're actually using the Loglinear rescorer, you then say, well, why not incorporate some other features as well? And we, in fact, actually wound up incorporating about 10,000 features that had to do with the conjunction of repair boundaries and syntactic phrases. So, as I said, repair boundaries don't always appear at syntactic phrases, but they often do. They often like to appear at the beginning of sentences, beginning of clauses, things like that. Wow. Does that mean it's time to go, right? Yeah. Okay. Right, yeah. So anyway, so there's the model, right? You know, the input sentence is then fed through the noisy channel transducer. It turns out that the transducer with a bigram language model can be efficiently inverted, and so you can use a dynamic programming algorithm to extract the 25 highest scoring parsers. We then parse them all using the generative parser. That gives us parsers and parse probabilities, feed them through the MaxEnt rescorer, and that gives us the most likely sentence in the parse. So just to sort of show some basic results. This is the noisy channel model with the bigram language model. Over here are F-scores. Higher is better with F-scores. Lower is better for error rates. So what you can see is that, in fact, actually is that, again, we're talking about either a bigram or a parsing model trained off a couple of million words of the switchboard data. So you can see with the parsing model, we actually get slightly better performance. But we get best performance of all if we use the MaxEnt rescorer plus the noisy channel model and the parsing model and the bigram model. I didn't say that there, but use everything thrown in together, as you would expect. Yeah, so that's all very well. In fact, we actually participated in the RTO4. This is a DARPA competition. In fact, I think it was the last one on metadata extraction. Greg would probably know better than me about this stuff, right? So we really only were sort of drafted in at the last moment when ICSI and University of Washington needed something to try and detect these speech repairs. Yeah, and we only really actually got to see the speech data for a small amount of time, in fact. So the test material was actually unsegmented speech recognizer output or transcripts. We competed in both of those. And then ICSI, SRI, and University of Washington supplied us with a whole bunch of features which they're acoustic feature detectors and boundary detectors and acoustic interruption point probabilities. I mean, all sorts of stuff like that. One of the great things, of course, is working with this MaxEnt rescoring framework is that it's actually fairly easy to incorporate features that just correspond to all of these things. They just are new features that you add into the bucket. And even though it was sort of thrown together at the last moment, we still actually won all of the competitions, all the disfluency detection competitions that we competed in. Okay, all right, so I'm conscious of time running out, so let me move on to the last topic. This is a topic of active work that we're working on here, and it's actually something that I'm really rather surprised works at all. In fact, this was supposed to be a baseline study that we expected would return null results and that we would actually start doing something more sophisticated based on them now, but the baseline itself actually did much better than it deserves to, we think. Okay, all right, so the rescoring parsers trained from hand-parsed corpora. These are small and expensive, right? And so, of course, one thing that people often think about is to say, okay, well, look, you've actually got a parser here. Why don't you use it to parse a whole lot of unparsed text and use those trees as input to the parser, right? And the received wisdom, which I, until a year or two ago, would have actually given to you if you would have asked, I would have said, aha, well, this sort of self-training improves the language model, but it doesn't improve the parsing model. And there's no real surprise about that because the unlabeled data is really giving you more information about the distribution over strings, but it's not really telling you anything about the distribution over trees, right? The only information you're getting about the distribution over trees from the self-training is information you've got from the parser itself, right? And in fact, actually, for the cynics in the audience here, I'm not looking at anyone in particular, right, that think that all these parse trees are just arbitrary figments of linguists' imaginations, you would say, yes, in fact, actually, it should be impossible to learn anything from the strings alone, right? I mean, if the trees are just sort of arbitrary decorations that linguists put on here. So the surprising thing is that this self-training, in fact, actually reduces the error by over 10%, which is pretty big in this thing here. So basically, the self-trained generative parser, the rescoring parser is getting around 91.3, and we can go up to about 92.1. Yeah.
Is this using your T-star of the lung cat?
So I'll actually show you what I do. So basically, the
It's using the n nearest to the. No, it's not.
So what we're going to do essentially here. I've got a. I think here's a slide here. So this slide here is actually sort of showing how the thing works. So we train up the generative parser and the parse rescorer just simply on the Wall Street Journal data. We take a bunch of North American newswire data, feed that through. This is generally, up to around 100,000 sentences. So that's about 20 times the size of the Wall Street Journal data. And so we produce a parsed NTC corpus. And to get optimal performance, we then actually, this is the experiment that I thought wouldn't work, right? So we then take that, combine that back with the pen tree bank. This is 20 times the size of the pen tree bank, so to make it at least not completely ignore the pen tree bank, we just include 5 copies of the pen tree bank in here. This forms our self-trained, what we call the self-trained training corpus, right? Because it includes a lot of parse trees that the parser itself has produced. And then we just run that back through the generative parser training procedure, and we then produce a new self-trained generative parser.
Or self-trained rescored parser.
And then, in fact, so we have not found any advantage to training the rescorer with this generative model here. So I don't know why that's the case. That's what I'm saying here. So basically,
So the only difference is you feed it the 50 best self-trained
That's
parsers,
right.
But then you use the same rescorer on it.
That's right. That's right. Okay, yes. So here are some of the results again, right? So there's the generative parser at 89.7. The self-trained generative parser is at around 91. So it's still not as good as the rescoring parser. So at this stage, you'd say, aha, the self-trained generative parser is in fact actually, maybe all you've done is just simply move information from the rescoring parser into the self-trained generative parser. We'll actually see in some situations that does seem to be happening. But then if we actually use either, here this result is actually from using the same rescorer that we used up here, but also we get around the same results if we retrain the rescorer. It seems as if there's really no difference which rescorer you wind up using. That I don't know why. Something else that's also surprising is that these things seem to be surprisingly domain independent. So if the first stage is trained either just on, this is the pen tree bank, Wall Street Journal plus the North American Newswire or Brown, right? And then now if you use just the first stage alone, right? So actually I think the Brown results are the most interesting ones here, right? So what's interesting is that certainly using a Brown trained parser on Brown is better than using a Wall Street Journal trained parser on Brown. But Wall Street Journal plus North American Newswire actually does better than Brown, which is really strange, right? And in fact, actually, if you do the whole thing with the rescorer, then in fact, actually the Brown with plus a Brown rescorer does slightly better than Wall Street Journal plus North American Newswire over here. But the difference between using the Wall Street Journal trained rescorer and the Brown trained rescorer on Brown data is, it's really not that big, right? I mean, it's sort of surprising, as I said. I mean, I would have thought that we would have been overlearning to the training data here, but in fact, actually, it looks as if this self-training is actually making the parser broader coverage. Okay, self-training only seems to work if the corpus, the self-training corpus is parsed by the rescorer. So you could just try self-training just using the generative parser's own output and not run it through the rescorer. And this is actually the sort of result that you typically see with self-training. So here, this says 1, but in fact it's really 0. There's no self-training data added here. And you can actually see as we add thousands of self-trained sentences, that's what this should really read, I guess. You can see if they're parsed by the generative parser, overall accuracy drops. Whereas if they're parsed by the rescoring parser, accuracy goes up. This red line here is sort of typically what people get when they try self-training. So the rescorer seems to be crucial there. In terms of actually what's producing the results, these are some sort of analyses over here. So this is sentence length marching along here. And this is just the total number of nodes, in fact, actually in the gold standard trees at each of these lengths. This is the number of nodes which the generative parser gets incorrect versus length. So you can see, and those of you that can't read these numbers over here, this scale here is about an order of magnitude smaller than this scale up here. Right? And so, in fact, you can see, there's basically on the relatively short sentences, there's not terribly nodes that we're getting incorrect. And so those sentences are relatively easy. And then down here, this is the reduction in the number of incorrect nodes due to self-training. So if I can compare the rescoring parser without self-training to the rescoring parser with self-training, you'll actually see that, most of the gain is actually appearing at sentences of moderate length. In fact, we sort of call this the Goldilocks effect. That these sentences over here are too easy. We're already basically getting them right. There's not too many nodes that are wrong here, so there's just not too much opportunity to make much improvement. And these sentences over here are so hard, they're the long ones, that who knows, right?
Triage.
Yeah. Here's the same thing versus number of prepositions. Again, the thing you want to look at is this thing down here, right? So again, it looks as if there's not too many prepositions, we're not getting too much improvement. Number of conjunctions. Again, also, this is sort of relatively surprising, right? So this is the number of conjunctions, number of trees with 0 conjunctions, 1 conjunction, 2 conjunctions in them in the training data. Actually, the total number of nodes in trees. This is the number of nodes that are incorrect. So you can see we actually sort of proportionally are more likely to make a mistake if a sentence contains a conjunction, which is sensible since coordination is very hard. And what's actually sort of kind of interesting is that we do seem to be actually getting more correction in sentences with coordination in there. So it's sort of surprising that this actually seems to be helping us actually learn coordination. Now, this is actually probably the most interesting of all of these slides over here. One reasonable hypothesis is that, in fact, what we're really learning here are things like these head-to-head dependencies, these linguistic dependencies. And we know that 1 million words of training data is really not enough to learn which, these lexical head-to-head dependencies. And so maybe, in fact, actually that's what we're really learning from this unlabeled data. And there is some evidence that that's the case. So over here, this is these numbers down here are the number of head-to-head dependencies which were not observed in the training data, that is in the Wall Street Journal, but were observed in the North American Newswire corpus, that is in the unlabeled data, that also appear in each sentence in the evaluation data, right? So, and what you actually sort of notice over here is that, I think this is the key plot down here, if the sentence doesn't contain any head-to-head dependencies that we had observed only in the unlabeled data, we actually are not likely to improve its performance via rescoring. But if it contains a few over here, we are in fact actually likely to improve. Now, I'd really like to end on that slide, except that we also get the same sort of improvement for unknown bigrams, and I don't really have a story as to why. Again, if the test sentence contains bigrams that were only seen in the unlabeled training data, we're likely to actually improve its accuracy.
Because most head-to-head dependencies are bigrams.
Yes, and I was actually even thinking maybe it's because the head-to-head dependencies that we get right may be very short range. That's the sort of, I think that's, in other words, if there's a head-to-head dependency that's really long, maybe we're not really certain to get it right. Okay, so almost done here. So which features, and this is the last sort of topic here, right? So we know that self-training just using the generative parser alone doesn't work. We know, so that means the rescorer is somehow crucial. Maybe a subset of the rescorer features are actually crucial for self-training. And in fact, we actually know from work in co-training that alternative views may, in fact, actually be extremely useful. So the idea is going to be, I'm going to experiment by changing the features that the rescorer uses, the self-training rescorer uses, and measure the effect on self-training. So basically, when we're doing the parsing of the unlabeled data, I'm going to parse it with a crippled rescorer. And in fact, I'm going to cripple it in two ways. I'm going to either incorporate only features in the rescorer that essentially mimic those inside of the underlying generative parser, versus I'll have a rescorer that only includes features that are unlike the ones in the generative parser, like those edge features that I was talking about before. And then we'll also look at all features, which is the combination of all of them. So if we look at the how the performance just simply of the self-trained first stage improves versus adding more unlabeled or parsed unlabeled data, what we actually see is that roughly speaking, all of these different rescorers all improve performance, right? So add more unlabeled data, the first stage generative model improves. However, we see a really interesting sort of divergence between the performance of the overall model. So remember, after we've trained the generative model, in order to get best performance, we feed that back through the rescorer again. So now when we feed that back through, again, the rescorer that uses all features, the only thing that's being varied is the rescorer that was used to produce the unlabeled training data. If the unlabeled training data was produced by a rescorer that used either all features or the shotgun features, we get the overall system performance. Whereas if the rescorer only used the generative features, this is essentially that flat curve that we see before, that we typically see with self-training. So that seems to suggest that these shotgun features, right, these features that are unlike the generative model, are really what's actually doing the performance enhancement for self-training. Okay, all right, so thanks for bearing with me through this talk. I apologize for running over. I guess the points I'd like to make is that I actually really do believe that the choice of features are probably the biggest determinant of parsing accuracy. If you gave me a choice between using a really good feature set and average perceptron or some sort of fairly generic machine learning algorithm versus a lousy feature set and the latest state-of-the-art machine learning algorithm, I'd take the best features. I think something else is that the details of the representations seem to be unimportant so long as you can compute the features, which displeases the linguists. In terms of practical results, I think what's interesting is that this combination of coarse-to-fine computation and conditional discriminative estimation, in fact, actually work extremely well together. This makes it practical to estimate very, very large models, which contain very, very complex feature dependencies. Seems to be high accuracy, and the reason why I included the speech stuff is because, in fact, I think it shows that this general framework sort of generalizes to other applications in a fairly straightforward way. And I think there still are some surprises in all of this stuff, even though, as Ken, I think, likes to say, people have been working on parsing for 50 years. There still are some other things, still are things there to learn, like why does this self-training work at all? And if we can understand that, how can we make that work better? Thanks very much, guys. Yes?
Mark, I was really taken with the slide where you looked at where you had the unknown bigrams versus known bigrams.
Right.
Have you tried the experiment of using that as a simple classifier to decide whether you should use
Yeah,
the original parser or
yeah.
the trained parser?
Yeah, so that's in fact actually exactly what we're doing right now. I mean, we got these plots. I mean, the work on this, we started that work just before I came to MSR, and it basically stopped for that year. And so now we're actively doing that again, and we're hoping to have an ACL paper about this stuff. But yeah, that's exactly what we're trying.
Actually, did you get an even stronger effect from bigrams?
Yes, I think so. I think so.
It looks like a
So
simple classifier that says
that's right.
If you've got fewer than 2 bigrams,
That's exactly right.
Don't use
That's exactly what we're. So we are trying exactly that. The only thing is to note, there's actually compare the amount of area here versus area over here, right? I mean, there's I mean.
But you'd get.
I know, but I'm just saying in terms of gain. All right, these are the number of nodes that we might expect to get, right? So the overall difference here is around 1 percentage point. My guess is that statistical significance in this stuff is around 0.2. In general, when we run our tests, if it's less than 0.2 difference in F-score, it's not statistically significant. So I'm hoping that we'll find that this will be statistically significant, but it's actually, the question is there 1/5 of the mass sitting in here as compared to over here? And I'm not sure that there is. But otherwise, yes, I think that it's exactly what we're doing right now. Yeah.
Mark, people need to go, I think. So
okay.
Why don't we conclude? And if you have questions for Mark, you can probably hang around for a couple of minutes and take them personally. Thanks.